This project uses an AT-Tiny84 and register-level programming to mirror the button presses on a keypad to a portion of an LED matrix. When any button is pressed on the keypad, the corresponding LED on the matrix illuminates for 300 milliseconds and then turns off. The AT-Tiny84 has 14 pins. It has two GPIO ports, port A and port B. Port A has 8 usable I/O bits and port B has 3. Each port is broken down into 3 registers. The data direction register determines whether each bit, corresponding to one MCU pin, is an input or output. A 0 in the data direction register for a specific bit sets it to be an input, and a 1 sets the bit as an output. The port register is used to set pins set as outputs either high or low, with a 1 or 0, respectively. The pin register is used to read pins set as inputs. If a pin is high, the corresponding bit in the pin register is a 1. If it is low, the bit in the pin register is a 0. This project uses port A to read the keypad input and port B to send data to a shift register which controls the matrix. All bits in port A are set as inputs with internal pull-up resistors, activated by setting the bits in the data direction register to all zeros and then writing a 1 to all bits of the port register. The keypad is a 3x4 matrix of buttons. There is one pin for each column and row. When a button is pressed, the corresponding row and column pins are connected together and pulled low, as the common pin on the keypad is wired directly to ground. At rest, the keypad pins are all high, as they are connected to the GPIO pins of port A with the internal pull-up resistors activated. When a button is pressed, an if statement in the code is triggered, and the column and row data is separated into separate variables that control the columns and rows of the matrix via the shift register, in order to illuminate the LED that corresponds with the button pressed. The matrix is an 8x8 array of LEDs, with 64 in total. To illuminate a specific LED, the corresponding column and row pins must be given a low and high, respectively, although the orientation of the matrix on the breadboard in this project inverts that. The first 7 of the 595 shift register's 8 outputs are connected to the 3 column and 4 row pins of the matrix in use. The column pins of the matrix corresponding to the column pins of the keypad are controlled by the first 3 bits of the shift register's output, and the 4 rows are controlled by the next 4 bits. The column and row connections between the keypad and MCU, and matrix and shift register follow the same system, with the first column pin of the keypad connecting to the first bit of port A, and the first column pin of the matrix connecting to the first bit of the shift register's output, and so on. This simplifies the conversion of the keypad input data to the matrix output data. The column and row data gathered, explained above, is combined into a single variable in the code and then shifted out to the shift register via port B using a custom-made low-level shift-out statement. A small delay keeps the LED corresponding to the key pressed illuminated for 300 milliseconds. An issue with this project is that minor ghosting takes place on the left side of the matrix in column 1. This is due to there being a connection between row pin 1 and column pin 6, which should not be the case. Likely a blown LED in the matrix has made for this connection, and it allows the signal on column pin 6 to influence the LEDs on row 1. Due to the nature of the matrix configuration, external conditioning resistors cannot prevent this issue, but replacing the matrix with one without damaged internals should fix it.